Hi folks, in the previous video I had talked to you about how to distinguish between a standard U substitution problem versus a slightly more complicated integration by parts, and seems like a lot of you found it useful. Um, However, it's somewhat incomplete. The reason it's incomplete is some problems do in fact look like the inverse trig and partial fraction problems also do look like a standard U sub or integration by parts problems. So since we have these various techniques, how am I going to distinguish which technique to use or what order to go in that uh, to come to that? So let me give you a way. I mean, don't take it as a strict rule, um, but first try to see if it is a straightforward use of problem. Then you really want to see if it is one of the inverse trig type of problems. Then look to see if it is a partial fraction. If none of these things happen, then you have to figure out a way to solve it by integration by parts. So this video primarily talks about the inverse trig functions and problems, but I don't want to talk about it exclusively because some problems you wouldn't know whether it is an inverse trig problem or it's a partial fraction problem. So I'll throw in one or two that look similar so that you won't be confused when you see these things in the test. You know what formula to use. So first let's look at the inverse trig formulas themselves. So you have on the left side different. If you take a derivative of sine inverse x, it's 1 over square root of 1 minus x square. Derivative of tan inverse x is 1 over 1 plus x square, and derivative of secant inverse x is 1 over modulus of x square root of x square minus 1. Sometimes you see in calculus people do drop off the mod x, so but still this is the right formula to use if you encounter a problem with just an x instead of a mod x. Now, so what does this well, I was talking about integration, but here I'm giving you formulas for differentiation. So what does this mean? So it means if I take this particular, if I am asked to integrate this, so the answer would be sine inverse x plus c. If I'm asked to integrate this, so and if I'm asked to integrate this, the answer would be tan inverse x plus c, right? And similarly this would be secant inverse x plus c. So I'm not trying to go into the basics. I expect that you know that, and you're coming to this video mainly to see which method to use in what case. So if this part is confusing, certainly you need to go back and try to understand what derivatives are or what integration is. Now, the most of the time I'll talk about these three only. The reason I'll talk about this is so that we don't clutter up the screen. If you take the derivative of cos inverse x, you see that it is just a minus in front. It's very similar to sine inverse x. And same thing, the cotangent, if you take derivative, it is minus times 1 over 1 plus x square. So the formulas are very similar. You should be able to recognize those. So just for sake of brevity, I'm going to use these first three uh, formulas and examples. But then you also need to know this. So you might be asked to integrate sine inverse x. These are the formulas you need to try to memorize, at least the first three of them. Now this I wouldn't be discussing today, as a lot of times when you see this, it's not very hard to identify that this is of this nature. The reason you get confused with some of these formulas is this: if you see, they look, if I'm trying to integrate 1 over square root of 1 minus x square, that looks like a regular algebraic problem, and you might try to figure out, try to do an U substitution for um, of a different kind, and you might go on the wrong track. So that's the main purpose for this video. So let's go down and look at a few examples. And before I do that, let's look at this formulas. So if integration of 1 over square root 1 minus x square dx is equal to sine inverse x plus c, and 1 over 1 plus x square dx is tan inverse x plus c, and 1 over modulus of x times square root of x square minus 1 is secant inverse x plus c. So I already talked to you about this on the top, but come to the right side. So you might sometimes see a problem like this. Instead of 1 minus x square, you might see 2 square minus x square, or 3 square minus x square, or you might here see instead of x square plus 1, you might see x square plus a square, where a is a constant. So how do you deal with this? This you could try to memorize these formulas, and some people in fact do that, and it could be useful. But if you are finding it hard to memorize this, just make sure that you memorize at least the thing on the left hand side. But then you need to understand when you encounter a problem, so that look like this, how to deal with it. So what you do in this case is you take the a out of the radical. You would write square root of a square minus x square as a times square root of 1 minus x square by a square. So you can see that that's the same thing, right? And then try to solve it, because now you notice it's in a format that is similar to sine inverse of x. Now the third thing that you would see in inverse trig functions that could sometimes be actually pretty confusing if you don't know how to solve this. So instead of look at this tan inverse x, it's 1 over 1 plus x square. Here I'm writing, if I have to integrate 1 over 1 plus a function of x square, and on the top I have its derivative, that you can still use the tan inverse x formula. So hopefully you can recognize this. So what I would do is I would say u is equal to f of x. Then if you notice, the formula becomes 1 over 1 plus u square du, because du is f prime x dx. Now we'll look at a few examples where you can see how we would do this conversion. But these are the types of problems also you would see. So I want you to recognize that. Okay, so this is that example that I talked about. You have x square over square root of 1 minus x to the power of 6. So if you had watched my previous video, the first thing you would do would be to see, is it a straightforward u substitution? What you would try to look for is, if I take the derivative of x to the power of 6, that would be 6 times x to the power of 5. Do I have that on the top? I don't. I have x square, I don't have x to the power of 5. So then my temptation might be to say, oh, I have to use integration by parts. But wait, before you do that, so look at these formulas. Does it look similar to any of them? Certainly it is not 1 plus x square, 1 over 1 plus x square, and it is not the second format of mod x times square root of x square minus 1, but it does look a little bit similar. I mean, not same, but it does look a little bit similar to square root of 1 minus x square, right? So what if I do, for example, in the x to the power of 6 that I see here. So what if I say my u is equal to x cube? So this formula becomes, in the bottom, it would become square root of 1 minus u square, and since du is equal to 3x square dx, I can write dx as equal to du over 3x square, right? So if I plug it in there, you would find that this terms out to be du. So this looks now very similar to this formula, so you can apply that formula. Now this problem is somewhat similar to this, but it's really exactly same as 1 over square root of a square minus x square. But if you didn't memorize this and you memorized only this, so what would you do in this case? You would have to write it as 1 over 2 times square root of 1 minus x over 2 square dx, and set your u is equal to x over 2, and notice that the formula looks similar to this, and then you can solve it. Okay, so now what about this? So this sort of looks like a problem where you can solve it using partial fractions, but you'll find out that if you try to factor it, you won't be able to do that. So here one way to we are trying to look for two numbers that when you multiply become 5, and when you add them they become 4. So you will actually find that if you can find two numbers that add up to 4 and multiply to anything more than 4, but I won't get into that, but you'll find out that you can't really do that. But you may recognize this, that this is similar to x. If you write this as x square plus 4x plus 4 plus 1, so this is equal to 1 plus x plus 2 square, and I can set u is equal to x plus 2. So then this formula becomes similar to this. Now again, if you want to go back to the order in which that I said you should try to solve this, first I'm going to see is it a straightforward u substitution, that is if I take the derivative of this, would I get anything on the top? I don't, because this would be 2x plus 4, and I don't have that on the top. So the next thing I'm trying to see is, can this be a inverse trig function of some kind? And it in fact is, and it doesn't work as a partial fraction because I can't factor it, but also I can definitely write it as something square plus something square. So that's the reason I would use this formula. So we are kind of running out of time, so I'll go ahead and solve the other problems in the next video. So you'll find that. I'll see you there.